Well, welcome to my second presentation. What I'm going to do today is give you a couple of examples of rather different types of problems that arise in motion planning. So we're going to see a spectrum of flavors of different problems, some of which look like pure combinatorics, mathematics, computational geometry, and then down to problems that use an approach that's more typical in artificial intelligence robotics communities, where people do a lot of proof of concept by simulation. And then finally, at the end today, I'll give an example of what happens when computational geometry meets robots in the hallway. What does it look like when we try to combine a kind of a pure algorithmic approach with working with people who like to move things around in practice? So what does that look like? So that's what we're going to see today, a variety of problems that relate to motion planning. So you recall that last time we talked about reconfiguration problems for linkages. So that looks decidedly mathematical. You have a chain of links. So in the language of the computational geometry book that you're probably familiar with, the 3 marks plus Ottfried, it's got very high dimensional configuration space, a chain of links. You have n links and -1 joints. You're working in a configuration space that could be parameterized by what those joint angles are. So it's not a Euclidean space. It's a space of angles, and there are many angles. So that's not a problem that you'd probably want to tackle with a configuration space approach. So what we did was try to work directly with the problem and see what we could say about which positions, which configurations of that chain could move between one another. We tried to establish equivalence classes of configurations. We say 2 things were equivalent if we could move continuously from one configuration to the other. So that was a flavor of a certain kind of problem. What do the configuration spaces look like? How many different configurations are there? Can you convexify a chain? If you can always convexify a cycle, then you have just one configuration space, one equivalence class of configurations. That was last time. This time, I'm going to change the model entirely, and we're going to look at robots that are modeled as a point. So they don't have any joints, just a point. And we're trying to move this point around. So in a practical setting, the point could be viewed as a reference point on some robot. And we're specifying how to move the reference point around. In that case, we're thinking of moving around a reference point. Then the 3 marks plus Ottfried would probably say, fatten up the environment by the shape of the object that you're moving, and then move that point in configuration space or in physical space past these fattened up obstacles. Compute obstacles in configuration space based on the shape of the robot. I think in that textbook it's a convex polygon. You're moving it by translation. Fatten up the obstacles so that you have kind of bumpers around them that ensure that when you move the reference point past these fat obstacles, you don't have any collisions in the physical space. So that's an approach. Here, I'm just talking about moving around a point. I'm not worrying about fattening up walls or obstacles or any of that, just moving a point. So we're going to illustrate 2 types of problems. One is the localization problem, and another is the navigation problem. So what are those 2 problems about? Localization problems. One type of localization problem says the robot already has a map of its environment. Maybe it's, as we're going to see in our example, we're going to use a polygonal environment like the floor plan of your university or your hallways. And it has some kind of equipment to help it find its way around. So it might have a compass, it might have a range finder so it can measure distances to the walls. Why does it need a compass, by the way? It's very handy to have a compass because if you don't know which direction is north and you're a robot and you're inside a square and you look around and see what you can see, you can't tell from that information whether you're looking at the north wall, the east wall, the south wall, the west wall. So you need some kind of compass to disambiguate situations, simple situations like that. But basically the idea is that this poor point is located, wakes up in some location within a polygonal environment and wants to know, where am I? I've got the map, where am I on the map? So those of you who are not from this university, you may have encountered that problem, trying to find the room, the hotel, the dorm, the lunch place. Where am I on this map? Here's a map. Where am I on the map? So that's a localization problem. I should just mention here that another very famous problem, or solution perhaps, is called SLAM. That's simultaneous localization and mapping, which was made very famous by Sebastian Thrun, the AI guy who led the team that won the challenge of having an autonomous car that drove from Los Angeles to Las Vegas through the desert and somehow managed to get there. But Sebastian Thrun says, well, you know, we can develop strategies for simultaneously creating a map and figuring out where we are on it. So I'm not speaking about that, but that's an expression that everybody should know is out there. It's very famous work. And the problems I'm going to talk about today, we do have a map. So creating the map is not the problem. If your robot lands on Mars, it's got to create a map for itself and figure out where it is as it moves around on that map. But that's not what we're doing here. We're saying we have the map and we want to know how to deal with it. Okay, so two concepts here that we're going to use is the concept of a visibility polygon and the concept of having some hypotheses about where we are on our map. So a visibility polygon is this. We have, I should just say here, by the way, I'm using some slides that were created by my students that I've modified. So what's going to happen is that text is going to come zooming out at us because they like to create slides with fancy features that I don't normally use. And so if I kind of jump back from time to time, it's because Malvika or one of my students has created some slides with things that come in. So I think that's about to happen. Let's see. So visibility polygon. So let me just get the zooms done so I won't be surprised. Okay, so here's a picture of our self-similar environment. It's a typical office-like environment. And thank you. And our robot, this red dot, wakes up and it looks around, and what it sees is its visibility polygon. It gets out its laser rangefinder, and it measures the distance to the walls, and it gets some shape like that. That's the visibility polygon of the robot, and the robot knows its position inside that region that it can see. Now, what it doesn't know is where that region is within the map that it has. So in this example, this visibility region and the robot is consistent with the hypothesis that the robot could be here. A robot here would see, it could just see along this corner here and see down this wall to this position. And if the robot were here, it would get the same visibility polygon in C and D. So in this situation, if our robot wakes up and gets that visibility polygon, we have 4 initial hypotheses about where the robot could be. So that's what we mean by visibility polygon, and that's what we mean by hypotheses. The hypotheses are A, B, C, D, might be here, 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 here. So the fun thing that we're going to do is think about how we would direct the robot around to determine whether it was here, 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 here. And you notice in this particular example, there's two little side corridors off to the left from the robot's perspective that are much lower for these two hallways on the right than they are for here. So if the robot, whichever hypothesis it's in, moves over to some position here, so it can look for this corner. If A sees this corner, if I tell the robot to move so it can attempt to see this corner, maybe it sees the corner, and then it would know I must have been an A. If I move and I start at B and I look for the corner and I don't see it, but I can see into this region here, I know I must have been at B. If I move over here and I don't see anything there, then I must have been at C or D. Okay, so if I were at C or D, if I don't see some kind of indentation here by moving, then I'm going to have to move further and see, well, which is it? Is it this one or is it this one? So I want to reason about what's a good strategy for disambiguating which situation we were in. Of course, someone who could look down from the top and say, we're at B, could tell this robot how to move around to prove to itself that it was at B. But we don't know that. We can't look down from the top. If we were trying to verify that B is correct, then we could specify a strategy. But we don't. We don't know which of these things is correct. And notice that we want to be very careful that as we instruct this robot to move around, we don't cause it to crash into the wall. Like here, if I tell the robot to move to the left and then go south and then turn left, and it happens to be starting here, it's going to crash into the wall. So I have to find a way of reasoning about the possible locations of walls and barriers, not knowing where I started from. So that's the problem. So generating the hypotheses, how do we, in general, go about figuring out where those A, B, C, D red dots are hypothesized initial locations? So the problem is this. We're given the polygon. We're given that green P prime visibility polygon that P sees, that the robot sees when it wakes up. And the problem is to determine all the points in the polygon that have that same visibility polygon. So in other words, we want to figure out those points A, B, C, D. And fortunately, this problem is solvable in low-degree polynomial time, and that's work of Gibas, Matlani, Raghavan in 1997. So that part is done. We can build on that. So the problem that we're going to look at is called the minimum distance localization problem. So this robot wants to figure out which of the initial hypotheses is the correct one, and it wants to do the minimum traveling around in order to answer that question. So we want something efficient. We don't want it to be making a long tour to determine the answer to where it is unnecessarily. The flying text. There we go. So we have our mobile robot that's placed in an unknown location in a self-similar environment, and it's got a map, a compass, and a range sensor. And we have those initial locations. And our objective, or initial hypotheses, our objective is to uniquely determine what the correct actual initial location is and minimize the distance traveled. That's the problem. So here's a computational geometry approach, more on the pure side. We're going to be talking about pure approaches down to simulated approaches down to moving a robot down the hallway. See that spectrum. So this is how a computational geometer interacting with a robotics guy might approach this problem. So here we are. We were able to prove that this minimum distance localization problem, when you express it as a problem of finding an optimal localizing decision tree, that's an NP-hard problem. And what do I mean by a localizing decision tree? Well, briefly, the idea is you have a plan for how you're going to move the robot around that's not interactive. It's just determined right from the start what your plan is. But your plan is going to have branch points depending on what the robot senses as you move it around. But you have to say your entire strategy right from the beginning. So at the root of the tree, you're going to say something like, move the robot, wherever it might be, 2 units to the left. And maybe that brings A or B or C or D to the top of this long vertical corridor. And so that might be the first thing you do. But then, from that vantage point, or maybe you go to the left and then down a little bit, you're going to sense the environment again and hopefully throw away some hypotheses. So you don't know which hypotheses you're going to throw away because the robot hasn't actually moved there yet, but you know that if you move to a certain position, you will be able to distinguish C and D from A and B. And you don't know what's going to happen to you in advance, but you can plan in advance. So you say, okay, I'm going to move to that new position, wherever it's going to be, and then I can see 2 things are going to happen to me. Either I throw away C and D, or I throw away A and B. So I get my tree branches depending on which of those 2 things happen. Now, if I throw away hypotheses A and B, what should I do next? Well, something different from what I'm going to do to differentiate C and D. So I get this branching tree that I design at the very beginning. And what actually happens depends on what the true location is, which I don't know. So this robot effectively is going to be moving around in this decision tree. And it looks very much like the hitting set problem. How do you diagnose something? You might do all the wrong tests until the very end, where the test that tells you which set you're dealing with or which illness the patient has, the right test to do happens to be the last thing you try. But there's no way you could have known that to begin with. So it's a situation that's similar to that. All right, so we want to minimize the distance traveled. And trying to find an optimal localizing decision tree is just a hard problem. However, there's a good competitive strategy for doing that. So, in other words, if you compare the worst case performance of what your strategy is going to be, take the ratio of that distance with what someone who could look down from above and see what the truth was all along, take the ratio of your worst case distance with the optimal distance someone from above could see, then that's a competitive ratio. So it turns out we could design a strategy that gives the best possible competitive ratio. So that's pretty much the best kind of result you could hope to get in this situation. So here's a concept we're going to use. We're going to use the concept of a visibility cell partition. Now watch out here, because we talked about a visibility polygon. Visibility cell is something different. Both starts with visibility, but they're different things. So a visibility polygon, that's what your robot can see. It takes its rangefinder, it finds out where the walls are that it can see, and it gets a polygon. But a visibility cell is part of a partition of your polygon into cells that have the following property. Wherever your robot is within that cell, all these points are going to agree on the vertices of the polygon that are visible from that point. So different points in here, they're going to measure different visibility cells. They're different distances from the walls and so forth. They're going to have different visibility polygons, but they're going to agree. Everybody in here can see this vertex, this vertex, this vertex, this vertex, maybe these two vertices, depending on your model of visibility, but they all agree that they can't see these other vertices. Okay, so where do these dotted lines come from? I claim that if I'm starting in this box and I move over to this line, all of a sudden I'm moving into a new region. The points in this cell can now see a different set of vertices of the polygon than these, right? Because what happens? Why is dotted line here? Well, this dotted line happens to be generated by these two vertices. What happens here is when I cross this dotted line, these guys can now see that vertex. And until I was cross the line where these two vertices align, points over here can't see this. Now, just as I cross the line, all of a sudden they can see that. So in order to generate the visibility cell partition, what I need to do is just extend I need to draw in the lines, the edges, that are generated by the reflex vertices being able to line up with the other vertices in the polygon. So here, this dotted line is coming from this and this. If I cross this line, now I can see this vertex. Oh, and also the extensions of lines. So if I cross this, now I can see this point, and so forth. So what's this coming from? Well, this vertex and this vertex. If I cross here, now I can see in the corner. But if I'm above this, I can't see the corner. So basically, that's the way you generate the partition into visibility cells. You extend the lines, the edges of your polygon, and you also put in the edges that are being generated by reflex vertex lining up with something else. I don't have a dotted line in here because this doesn't represent seeing any new visibilities. Okay, so visibility cell partition. It's different from what's a visibility polygon. So here's the sketch. Here's the sketch of the strategy for determining where your robot is. What do you tell your robot to do? So you're given the visibility polygon that the robot detected when it woke up, and we generate the hypotheses thanks to the previous work I mentioned by Gibas et al. And now we compute the overlay arrangement of the visibility cell partition. So what does that mean? Where's my picture there? Here's these. Can you see these dotted lines in the back? Yeah? Okay. So what I'm going to do is create multiple copies of this visibility cell partition, one for each hypothesis. And I'm going to pick some origin, doesn't matter where, and I'm going to move each copy so that the hypothesized location moves to that common origin in the world we're going to put. So I'm just going to, or if you think of it in just imagine the origin we pick is at hypothesis A, say. I'm going to take a copy of this picture and translate it so that B lies on top of A. And what's going to happen? Well, edges of the polygon are going to go slicing through cells, and cell edges are going to be slicing through one another. And I'm going to get a virtual world, a kind of dangerous place, because as I move around in it, I'm not sure where I'm going to bang my head into the wall because, I was at a hypothesis, a true location that says if I turn there, there's going to be a wall. I don't know where's going to be safe and where's not going to be safe. But if I look at this overlay arrangement of the visibility cells, I can be sure that no matter what the correct hypothesis was, within that subdivided cell, all the vertices will be, all the points will be able to see, will agree on the vertices that they can see, whatever they might be. Okay, so we generate the hypotheses, we compute the overlay arrangement, which starts to be computationally expensive, and we translate a copy, one for each hypothesis, one for each red dot possibility, to a common origin. And then here's the simple, greedy strategy. And we were absolutely astounded when this turned out to work. You simply move the robot to the closest point that rules out at least one of the hypotheses. You just move the robot to the closest point. So it's going to be on the boundary of one of these cells in the overlay arrangement where you get some information that allows you to say, okay, I'm not in hypothesis B. I ruled out at least one. So you don't try to rule out as many hypotheses as you can or anything like that. Just move the closest place that eliminates at least one hypothesis. That's the strategy. Now, interesting, we don't want to bang our noses, right? So I claim this strategy is going to be safe in the sense that we're never going to direct the robot into a wall. Why is that? Well, let's say a robot smashed into the wall. That would be new information, wouldn't it? That would tell you that you're in a hypothesis such that there's a wall there, and you're not in a hypothesis that doesn't have a wall there. So you're definitely not going to be going through any walls with this. That would be, a wall would allow you to rule out at least one hypothesis. Okay, so it's safe. So let's see, I think my big plan here was to actually do this in PowerPoint. Take this and just overlay it with this. But I'm going to ask you to imagine that because that's just too scary a thing for me to try to do in the middle of the slideshow, to move this to this. I don't know. The students can do these kinds of things. So just imagine what would happen if you took this and moved it on top of A. Then you'd see B. B's got this long channel, so you'd see a long channel, and then you'd see a bunch of things over to the right. You get some more complicated figure with 3 pipes sticking up and some lower corridor down here and some things happening in the middle. And I'm sorry, I don't have a beautiful picture of that, so I'll just have to invite you to imagine what that might look like. Okay, so the results of this strategy is that you can create a decision tree, so a plan once and for all, and a tree-like form that tells you what to do as you go from one location to another and rule out hypotheses. Depending on which hypotheses you rule out, what do you do next, and so forth. You can come up with a strategy like that has a competitive ratio that's k minus 1 times d. And here k is the number of hypotheses. So in the picture we've been looking at, we've had k equals 4 or k equals 2 in those little pictures. And d is the length of an optimal verification tour. So what's that? Start at your initial location and make a tour around and come back to your true initial location, at the end of which you will have been able to rule out all the other hypotheses as you travel around the polygon on this tour. So the complexity for this, it's polynomial, but it's order n to the 6th, which is not very attractive, where n is the number of vertices in the polygon. Okay, so computational geometry style result. we got to compute some visibility polygons and some overlays, and it looks like computational geometry. Okay, now here's a new approach. So new student, Malvika Rao. I'm using her slides. She's the one with the zoom-ins. And Malvika says, well, that's kind of unsatisfying because what we're doing, we're obsessing about the worst thing that could happen, the worst case performance. Why don't we just be sensible? So be sensible from a more robotics researcher perspective. We're just trying to get good performance, something that works pretty well in practice. And what does practice mean? Well, simulate. Do some simulations and you have a strategy that at least works well in simulation. That's the kind of idea. So one interesting problem that arises with this mentality about studying localization problems is that if you're going to do simulations and validate your theoretical results by simulations, you need to be able to generate random environments, random self-similar environments. So, you know, what self-similar mean? Well, environments where there are situations where the robot can't tell exactly where it is. That's what we mean by self-similar. So you need to do simulations, you've got to generate these environments. How do you generate a self-similar environment at random? No idea. So that in itself is an interesting thing to think about. How do you generate these? I mean, you could go to City Hall and try to get lots of floor plans for buildings. That would be one approach. We didn't do that, but you could do that. How do you generate them at random if you want to do repeated studies of how your algorithm works? Well, that's a problem. So I'll just say that when you take this kind of approach, you can't expect to do a very precise analysis. You can't expect to say we get expected running time or expected path length, something like that. It just doesn't make sense because you've had to generate the environments that you're doing the experiments in. So different. It's different. So what's going to be sensible? So actually I'm going to show you two ways of being sensible. The first way we're going to look at is called overlay intersection. So we kind of like to avoid the running time of computing an overlay of visibility cell partition. That's computationally expensive. So can we avoid doing that? So here's the idea. Consider only the connected component of the intersection region of the overlay arrangement. So nothing about cell partition. So imagine you have two hypotheses here. So you make two copies of this picture. And now you move B over on top of A. And when you do that, you see you're going to have a region here that has got some walls, because that's going to be the intersection of what A thinks it can move around in without bumping into a wall, and what B thinks it can move around in without bumping into a wall. So you intersect those two regions, and you look at the connected component that contains the hypotheses that have been mapped together, and that's going to be a safe region to move around in, no matter whether you started at A or at B. You're not going to bump into any walls if you do that. So it contains the origin, and it's an area that's known to exist, no matter which hypothesis might be the correct one. So by the way, these pictures, they look similar to one another, but you'll notice from slide to slide they change slightly, right? Sometimes we have four legs that stick up, and sometimes just two, and so forth. So okay, so here's the original shape, and now we mapped B to A. There it is, and now we look at the region that A and B both agree lives in their situation. So this is going to be safe to move around in. So let's just randomly sample points in this safe region. It's safe to move to any of them. let's just randomly put down some points in that region and then move to one of them. So which one do we move to? Well, we need a way to evaluate how good a point is, how useful it might be to us. So we need to have some kind of evaluation function for a point. So that's what we're going to do. We're going to have a set of R random sample points that are picked from this overlay intersection. And for each point, sorry about the color there, it says compute the value of that point. And what's the value? Well, it's up to us to define what we mean by how useful a point is. But I think what it says in the fine print is the expected number of hypotheses that we're going to rule out by moving to that point. And, that's the information. Sorry, that's the information. And I'm sorry, I don't know exactly what the yellow blur says. But you get the general idea that I'm trying to convey. You have values here at these points. And now you also have the distance. So the distance to each of those points. And of course, we're going to measure the distance by the distance within this safe region here that belongs to both the hypotheses. So maybe you get a lot of information here, but the shortest path to get me there is pretty long. Maybe this is not very far away, but I don't get any information there, and so forth. So I can normalize how much information I get by how much distance I travel, so I get kind of information per unit distance as a value of interest for each of these points. And maybe none of those points are useful to me at all. I don't know. Then I have to randomly sample again or increase the number of points I'm sampling. So this gives rise to what's called the Common Overlay Localization, or COL algorithm. So what we do is sense the visibility data, get that visibility polygon, generate all the hypotheses, so we have the red dots, and then compute the overlay intersection. That was the blue region on the previous slide, and randomly sample the points, compute the value of each point. That's the information per distance traveled to get there. And if there are not any useful points to us, if they all have value 0, then we just have to go back and try it again. Just keep repeating this. So we don't know in advance how many steps we're going to have to go through until we happen to pick a useful point. So this all gets to be experimental, something you have to experiment with to find out what works. And it's going to depend on the architecture of the floor plan, which we're randomly generating lots of examples for. So it's a very different flavor of problem. So then, once we find a useful point, we're going to move the robot to the point that has the highest value to us. And we just defined value out of the blue. It's not a precise mathematical, well, it is a precise mathematical thing, but we have to invent the formula. It's not like finding minimum distance or something. It's not very pure in terms of computational geometry. We have to say, well, it seems like a reasonable way to say how useful a point is. So then we eliminate the hypotheses that are inconsistent with whatever the robot can see at that point. It's going to be a useful point to us. Went to a lot of trouble to travel there. And now we throw away the hypotheses that point is able to help us rule out. It's useful to us. It means we can rule out at least one hypothesis, maybe several. So we rule out all those hypotheses. Now what do? We've got to repeat. We've got to go all the way back to 3, because now maybe we've eliminated D and B. So we only have 2 hypotheses. So now when we look at the overlay of the new set of smaller hypotheses, we're going to get a different overlay. So now we sample in that. And we continue sprinkling points until we get some useful point and travel to the closest one that with a high value. And just keep doing that until we're down to one hypothesis. Then we know where we are. So that's the strategy. It seems very sensible. Just travel around where you know you have a safe environment and just sample in there. Okay, now Malvika is going to get even more sensible. Let's see. Okay, so here's an illustration. Okay, so here's a step-by-step. So computing, for this example, a little bit more complicated example, the region, this blue region, represents something that is consistent with each hypothesis. Each hypothesis could have this blue figure put in it without bumping into a wall. So we're gonna sample those points and then measure the how useful they are to us. And I think we're going to see a choice. Yes, okay. So this is a point. Let's see, these points, they're totally useless, right? I don't get any information by traveling here because I can't see any corners that are different, that distinguish amongst those hypotheses. So some of those points are totally useless. But now here's one. This point, let's see, this point's pretty useful, potentially. Let's see, you can see all the way down to here. Well, no, this point can see all the way over to here. I don't know, it's not clear that this point's useful. Well, yeah, it is. Because if I were here, for example, and I moved over here, and I looked down, I couldn't see anything, I would know that that it couldn't be in A or C. I would have to be in B or D. So yeah, it would be useful. So okay, here's a point that's useful. Why is that point useful? Well, it can tell the difference. It's got a long corridor it can see down. If I happen to be in B, I wouldn't get this long corridor. I would get a short distance to the end of the wall. So this point in the overlay arrangement is going to be able to tell the difference, instructing the robot to go here and then here relative to the initial location, is going to distinguish between hypothesis A and hypothesis B. It can't be B. And it can't be D either, because if it's D, then I don't see this long corridor looking in that direction. Okay, so X out, the B and the D. Now it's between A and C, which is the correct hypothesis. So we recompute the overlay arrangement for just A and C. The connected component that contains A mapped on top of C looks like this. And now we're going to randomly sample in there. And here's our present location, this red dot. And so when we are evaluating things, we're using the distance from the current location to those new locations, some of which are not helpful at all. Going up here doesn't help us. So what do we do? So we generate a path like that, for example. And then from there, if we're able to travel down to here, that should help us rule out both. Let's see, we ruled out B and D before. It rules out C, because let's see, if we were over here, I can see a long way here, and if I were in the corresponding position here, I wouldn't be able to see so far. So I can narrow it down to having to have been at position 8 to begin with. Yeah? What? When I put C over A, then D is over. And I don't know why this one isn't covered. This can also work there, no matter where it's over. Yes, that's true. That's true. Yeah, it's it would be better to have more slides and more figures here for sure. Yeah, this can fit here and here. The only eventual reason is just for the sake of not using so many slides. This turns out to be the answer, so it's. But you're right. It fits. This fits with both this position and this position, but we're able to rule out this C and just come down to this. So it's just skipping a step. Okay, so here's a second strategy for being sensible. And it says this, start just like we did before, compute the visibility polygon, generate the hypotheses, but this time, and here we're going to use a little bit more computational geometry. We're going to say, look at the edges that aren't polygon edges, but are edges of that overlay intersection region, and compute which points can see them. So compute the weak visibility of these edges. And then take the union of those polygons that we generate. And so we get a region here that can see these edges, some point on those edges. And so let's just sample points in there because we know those points are going to be useful. They can see some point on the boundary, this artificial boundary where we don't have a wall of the polygon, but we do have a wall of the intersection overlay region. So let's just sample in the regions that we know are useful. And we're not going to waste sample points up here that don't help us. That's the idea. So again, we compute a value as before, defined somehow, and we move the robot to the point in the useful region that has the highest R value. So same strategy as before. Eliminate hypotheses. So we should definitely be able to eliminate a hypothesis depending on what kind of information how we see the wall, and then keep repeating those steps until we only get one hypothesis. So that's the idea. A similar idea, but just being even more sensible in an intuitive way. So there we start at A. This is the mapping A and B together to a point as a single origin. And then here's the region that we know is consistent with both A and B. And the green is a region of points that can see some point on one of those boundaries. We see this. These points in here can see this edge, and these points in here can see that edge. So we get something useful there. Okay, so compute the useful region. Let the set of internal edges be, say, set B, and for each edge of those internal regions of your overlay intersection, compute the weak visibility polygon, take the union of all those, and get this green area there where we do the sampling. Experimental results. Okay, let's experiment and see how well this works. So that means we need to generate an office-like self-similar environment. And here's the type of thing Malvika came up with. I think she generated these by starting off with a grid, essentially, and just deciding randomly to remove some of the grid cell edges. So she gets something that looks very grid-like, which is, well, it looks kind of self-similar and office-like. So she tried this on 20 different environments. So she keeps generating things that look kind of like this. This is just one example. And they each have 400 vertices in them, so pretty large office environment. And she picked 3 different initial locations, and then depending on the initial location, she did 20 different trials to see what would happen. And here she's looking at the average path length divided by near optimal path length. So near optimal path length, you can hope to get by just continuing the process for a long time, using lots of points, more and more points, so you get a pretty good idea what the optimal path length is, which she normalizes by that. So optimal path length down here is 1.6. So if you're not sampling so many points, then initially with few sample points, you're getting something like 1.6 times the shortest localization path you could find. But then it starts to drop, and you get some experimental curve that's saying for that situation, for those types of environments, you get down to around 500 random points, and you got something that looks pretty good. All right, what happens if you try the other strategy? Okay, so here's another picture of a randomly generated self-similar environment. I'm not sure this is so randomly generated. Actually, this looks like the NP hardness proof that came from the earlier paper. This figure there, the idea was it's hard to come up with a good localization strategy if you build yourself a very long staircase. So it's a long distance from here to there. This picture, the geometry doesn't quite show this, but imagine these Fs are just tiny, tiny little pieces sticking up on these steps. Now you could figure out where you were. If you ran up to the top step and counted back, you could figure out what step you're on. But if you make the steps long compared to the heights of these pieces, then you're better off exploring these pieces on whatever step you're on than trying to run to the bottom or the top. And so you get pictures like this for showing that it's hard. If you want to have some kind of signature, like maybe make one of these pieces a little shorter than the other or something, and everything else is the same. So you have a lot of these Fs on each step. Basically, there's nothing you can do other than pick a corridor to explore and hope for the best. See if you find the short piece there, and then you know which step you're on. Have a little short piece that tells you which step you're on. But you don't know what to try first. If you have a lot of these things, anyone's equally attractive. And so in a worst case, you could wind up running down lots of these corridors in order to determine which step you're on. So you're stuck with worst case scenarios like that. So here she's doing experimental results on something that looks like one of those worst case scenarios that we designed in previous work. All right, so what about the URL algorithm? So that's the useful region localization algorithm, where we said, let's just sample points in the region that we know is going to be helpful to us. And here the shape of the curve is, as you might hope for and expect, quite a bit better. You don't have to sample very much at all before you have pretty much the optimal length path. So you get a rapid reduction in the path length by just sampling points you know are going to be useful. Here's another experimental scenario using that other type style of generating office environments. So comments, okay, so 2 new algorithms for minimum distance localization. This random sampling strategy seems to be useful, but that's a very qualitative term. It's not a kind of computational geometry. B, the asymptotic running time, the exponent just came down, so it's better than the other algorithm. We don't get any kind of result like that. It's just something that's qualitative. And just with the types of environments she was generating, it seemed like you didn't have to generate so many samples before you got something that was compared favorably to the optimal value. And the useful region localization beat out the other strategy. And also one observation is that the theory is helping here. I mean, from the point of view of someone who wants to be sensible, theory might look very esoteric and useless, but notice that it's contributing some very useful concepts for this more applied strategy. It's the idea of generating these hypotheses, using an overlay arrangement, using weak visibility from an edge. Those aren't ideas necessarily that are going to occur to a robotics colleague. It's just not the way people moving around robots think. So it was an interesting combination of points of view here, doing simulations, but also informing the strategy by concepts from computational geometry. And I mentioned generating self-similar environments is a tricky thing. Okay, so let me just skip to, complexity analysis. One of them, you can't even say what the complexity analysis is because you don't know how many times you're going to have to keep sampling till you get something useful. And the other one, at least you can say something about the running time. So let me just skip quickly to navigation down the hall before we go to lunch. I won't say much about this other than to say the world looks different as you move from theory to simulation to actually trying to move something down the hallway. So here's our little experimental robot. So we don't have a lot of research funds, but we have enough we can buy a vacuum cleaner robot. And it's got a laptop that's rides along on top. And it's got a little plastic box that's got the sensing devices and the radio transmitter and the gear that goes along with the robot. And the problem that we were looking at this time wasn't localization, but this. You plan, you're going to move down the hallway. We're going to go to lunch. We're going to go out the door, turn left, walk. So we know what the path is in the environment. But we're going to need some help if we're a vacuum cleaner robot not veering off course. We deviate a little bit from the planned path, and we get totally lost. We start crashing into walls and all kinds of bad things. So the question becomes, if you're going to navigate with the help of some devices, instruments that you put in the environment, where should you place them? You have beacons, say, that are going to help guide this robot. Where do you place the beacons? You don't have a big research budget, so you're not going to just put hundreds of thousands of beacons. Maybe you're going to put 10 beacons or 15 beacons. What's the strategy for placing them in a polygonal environment? Of course, in Victoria, we have lots of water. We're interested in the oceans, and we're doing underwater robotics. Where do we place sensing devices to help guide robots underwater? Well, that's getting things to work in the lab is a start for tackling a bigger problem like that. So we want to position range-only beacons. So you're going to measure the distance to a beacon. And we want to know where we're going to place those things. So if I'm going to go down the hall and turn left, I got 3 beacons, am I better off placing them there to help me get around the corner? Or should I spread them out like that? There's questions, and there's potential strategies. So this is a problem that's attracted quite a bit of interest at places like ICRA, the International Conference on Robotics and Automation. So what we were trying to do was use ideas from computational geometry, again, to help suggest what could be good placements for beacons. And we wanted some placements. So you're going to use some kind of search strategy like hill climbing. There's infinitely many times infinitely many placements where you could put your 3 beacons, right? So you have to have some strategy for rapidly evaluating how good a particular pose, they call it, placement of 3 things, position information, and then using hill climbing, you have some way of evaluating, put a measure on the quality of this, the helpfulness, the utility of putting your 3 beacons in those locations, and then you want to know, okay, if you move them a little bit, are you getting better or worse utility, and so forth. So you want to be able to rapidly evaluate some notion that you come up with of the quality of a placement. So the idea we had, and it seems so reasonable, although our experiments didn't go far enough to really say much one way or the other, was that if your beacons are such that, well, first of all, you want your robot to be able to be in contact with the beacon everywhere along the path that you want. So you like enough beacons. If you don't have enough beacons to get you around the corner, I mean, you're just not going to make it. But if you have enough beacons, you'd at least like to spread them out so that each point on your desired path is in the cone that a beacon has, where it can communicate with the robot. And now, so in this picture, you see these 3 beacons, and you see their cones, and they're placed when you position not only the beacon, but you adjust its orientation, so you know where these cones are. So there's some regions here, like this one. This region is seen by 3 different beacons, but on the other hand, it's not in the convex hull of the beacons. So we were thinking, so we call this being, points in here are well seen but not well heard, or maybe we called it well heard but not well seen, whereas in here we have, in this region here, these points are in the convex hull of the 3 beacons, and they're also in the 3 cones of the beacons. So that seemed like a really good area to aim for. So one strategy might be you kind of try to go along your path and aim for places where you have a lot of information. You can really interact well with at least three different beacons. And so now you can say, okay, where am I within a region like this? And you can get you can make precise again your knowledge about your position. We'll talk about reasoning about uncertainty, dealing with uncertainty in geometry. Here's the situation. Navigation, the wheels slip. Oh, it goes from carpet to smooth floor, things like this. All kinds of batteries weaken. Things happen to take you off course and make you not where you intended to go. So if you can aim for kind of hot spots where you can get precise information of where you are again, then you can adjust your position, how you go to the next hot spot. That was the idea that we played around with. So we had a little utility function here. So this is just coming out of the sky. We're just making up something. If you have a point in your environment that's not covered by any beacons, we say that's got 0 utility. 1 beacon, 2 beacons, and then you get a lot of points if the point is if the position is well seen and well heard by your beacon placement. So then you evaluate your path and see how good a path it is with respect to a particular beacon placement, and try to improve the placement of the beacons. So I won't go into any more detail than that. There's some simulation results that don't have anything to brag about. There's a little picture of our experimental setup. And I must say the computational geometry students had a huge amount of fun playing around with students who had taken mechatronics courses and could design equipment like this. And yeah, it was very instructive. Omnidirectional beacon. This omnidirectional acoustic receiver is just a styrofoam ball that directs the signals to the receiver. So there's our hallway. Here's a beacon set up in the hallway or aimed in a certain direction. And there's what our hallway looks like. This is an actual picture. So it's looks of the floor plan, and there's hot spots. And then we looked at trying to decide how to design an experiment to test the strategy is yet another problem. You create some waypoints along the path you're trying to follow, And at each waypoint, you stop the robot and see how far off course you've gotten according to some measure. And you do that repeatedly. So you see if some beacon placements are better than others measured by this waypoint strategy. Okay, so thank you very much for listening. And that concludes my second talk.